Hello friends, in previous lecture we have started the gear measurement chapter. Now we will continue further. The slide is regarding classifications of gears. Gears are commonly classified according to the position of the axis of the shaft between which the motion is transmitted. Types of gears on the basis of orientation of shaft axis. First one is parallel axis, intersecting, non-intersecting and non-parallel. In parallel, there are three types of gear. One is spur gear, helical gear, rack and pinion. In intersecting, there is an bevel gear, and in non-intersecting and non-parallel, worm and worm gear, spiral and screw gear. Now we will understand details about the gears. First one is spur gear, as shown in figure here. It is the teeth of gear wheels are parallel to the axis of wheel. The gears are called spur gear. They transmit power from one shaft to another shaft, as shown in figure. Spur gear. Helical gear. In helical gears, the teeth are inclined to the axis of wheel, as shown in figure. The axis of the wheel is like this and it has some incline. Teeth are inclined. The gradual engagement makes them operate much smoothly and quietly than spur gear. Here figure shows the single helical gear and double helical gear. Here the angles are different. It's also known by herringbone gear. Next is rack and pinion, as shown in figure. Pinion here and rack. It is a special case of spur gear in which one gear is having infinite diameter called rack. Here this is rack, a flat uh, rod on which teeth are there, which is in infinite. They are used to convert rotation into linear motion. Next is bevel gear. Teeth of bevels are cut on conical surface, as shown in figure here. They are useful when direction of the shaft rotation needs to be changed. Here the rotation of one shaft is here and here it is different. Bevel gears are generally used to transmit power at perpendicular direction. One here, one another type is spiral bevel gear. Worm and worm gear. It is a gear arrangement also known as worm drive, in which a worm meshes with a worm gear. They are used when large gear reductions are needed. Here the figure shows worm gear and worm. Spiral or skew gears. Spiral gears are also known as cross helical gear. They have high helix angle and transmit power between two non-intersecting and non-parallel shaft. Here it shows non-parallel and non-intersecting shaft. Next slide is regarding measurements of gears. The inspection of the gear consists of determining dimensional accuracy during manufacturing using the following methods. First is general test, in which gear profile inspection, involute measuring machine, and other is rolling gear test, that is a Parkinson gear tester. Other methods, measurements of individual elements are measurement of gear tooth thickness. There are three methods for measuring the gear tooth thickness: gear tooth vernier method, constant chord method, and tangent method. Other is measurement of pitch diameter and tooth spacing. Then measurement of gear pitch. One by one we will understand in detail. First is gear general test, in which involute measuring machine. In this method, the gear is held on a mandrel and circular disc of same diameter as the base circle of gear for the measurement is fixed on the mandrel as shown in figure. After fixing the gear in the mandrel, the straight edge of the instrument is brought in contact with the base circle of the disc. Here it shows this is the gear and here is this plunger moment and stylus. Here it is, and here one dial indicator is located. Now the gear and disc are rotated and the edge moves over the disc without slip. The stylus moves over the tooth profile and error is indicated in the dial gauge. Here the movement of this stylus will be like this and the measurement will be done. Moving to the next slide, rolling gear test. It is popular gear testing machine used in metrology laboratory and tool rooms. The gear being inspected will be made to mesh with a standard gear, that is master gear, and a dial indicator is used to capture radial errors. This test is generally performed on a most commonly used machine called Parkinson gear tester as shown in figure, the arrangements. Now we will see the working of this Parkinson gear tester. This test is used to detect the any errors in gear like tooth form, pitch, coincidentity of a pitch line. When two gears are in mesh with each other, then any of the above errors will cause the variation in center distance. Radial variation of the gear being inspected are indicated by dial indicator. The variation in the variation is plotted on a chart or graph sheet which indicates the radial variation in the gear for one complete rotation. As shown in figure 1, there is a master wheel which is fixed, and one there is an movable gear wheel which is under test, which we have to test. Here it is movable in with the help of some spring arrangement. Here scale is provided and one dial indicator is provided. Once it starts rotation, the if any variations are there, there will be a movement of this spindle in this direction, and that is recorded with the help of dial indicator and some plotter graph arrangements, and the measurements can be done of tooth form, pitch, and we can also find out the concentricity of the pitch line. Now moving to the next slide, it is measurement of individual elements. Measurement of gear tooth thickness. First is gear tooth vernier method. This method use caliper to measure gear tooth thickness as shown in figure. Gear calipers has two vernier scales, one horizontal and other vertical as shown in figure. Here one is horizontal vernier caliper and other is vertical vernier caliper. Horizontal vernier scale reading gives quadral thickness and vernier caliper gives the caudal addendum by measuring position of a blade which can slip up and down. Working. First, the blade position is set to a value equal to the addendum of the gear tooth and locked into position with a locking screw. The caliper is set on the gear in such a manner that a blade surface snugly fits with the top surface of a gear. The two anvils are brought into close contact with the gear and the caudal thickness is noted down on the horizontal vernier scale. The theoretical value of caudal thickness can be found out by considering one tooth in the gear and it can be verified. For theoretical, the equation is for caudal thickness of gear tooth along with pitch circle is m into z sine 90 degree divided by z. Next is for caudal height mz by 2 into 1 plus 2 by z minus cos 90 degree divided by z. Next is constant chord method. This method of checking gear tooth thickness measures the tooth width at the point of contact of a symmetrically placed closed mesh rack. The length of chord AB is constant for all gears of the same module and pressure angle irrespective of the numbers of the teeth. Single calculations and comparator settings will suffice with checking a set of meshing gears with different numbers of teeth. It is an efficient method for measuring a large numbers of gears, each having different numbers of teeth but the same module. Length of chord AB is given by C is equal to AB, here it shows pi by 2 m into cos square phi. For caudal height is given by D, here it shows is equal to m into bracket 1 minus pi by 4 cos phi into sin phi, where m is the module and phi is the pressure angle of the gear. Next is base tangent method. In this case, tooth thickness is measured by measuring the caudal distance over a numbers of teeth by using a tooth span micrometer, also called a flange micrometer. The base tangent length is the distance between the two parallel planes which are tangentially to the opposing tooth flange. Base tangent length across s numbers of teeth for an involute gear is given by the equation, that is Ws is equal to m into z cos phi into tan phi minus phi plus pi by 2z plus pi into s by 2z, where m is the module, z is the numbers of teeth, phi is the pressure angle, s is the numbers of tooth space in Ws as shown in figure Ws, which is to be measured. Table for the span width for given value of module, numbers of teeth and pressure angle are used for faster inspection. Here they also shows the diagram of actual base tangent instrument micrometer. Now moving to the next slide, measurement of pitch diameter, which is important. Pitch circle diameter Pitch circle diameter and tooth spacing of a gear is measured by checking by inserting cylinders plugs into the tooth space so that their axis lies on the pitch circle. Here it shows one plug is inserted and PQ is measured. The cylinder diameter can be found by considering a rack in mesh with the gear. Cylinder plug diameter is given by PQ is equal to pi into m by 2 cos phi, where m is the module, phi is the pressure angle. Well, here we should take a note that the plug size remains the same for all gears having the same pitch and pressure angle. A correction will again have to be made in this plug size for backslash. Working: if a gear has an even numbers of teeth, cylinders can be placed in diametrically opposite tooth space and measurements taken then over them as shown in figure. Here the cylindrical plugs are kept both sides and measurements are done of pitch diameter as shown here. If a gear has an odd numbers of teeth, gears with an odd numbers of teeth can also be checked for pitch diameter by the two cylinder methods. In this method, the calculation is needed to find the pitch diameter, yes, shown in figure. Next is measurement of gear pitch. Pitch is the distance between corresponding point on equally spaced and adjacent teeth. The two types of instruments that are usually employed for checking pitch are pitch measuring instrument and pitch checking instrument. First we will see the pitch measuring instrument. Here is shown in figure. This instrument enables the measurement of cordial pitch between successive pairs of teeth. The instrument comprises of a fixed finger as shown in figure and a movable finger, which can be set to two identical points on adjacent teeth along the pitch circle. The pitch variation is displayed on the dial indicator that the attachment of the instrument. Here it shows it will indicates the movable of the spring and it will be noted. Then going to the next is pitch checking instrument. A pitch checking instrument is essentially a dividing head that can be used to measure pitch variations. Then the instrument can be used for checking small as well as large gears. Due to its portability, it has two probes, fixed which is known as anvil and measurable ferrule that is movable as shown in figure here. This is fixed and this is movable. Measuring feeler is connected to a dial indicator through lever. Working: the instrument is located by two adjacent supports resting on the crest of the teeth. A tooth flank is butted along the fixed anvil and locating supports. A tooth flank is butted against the fixed anvil and locating supports. The measuring feeler sends the corresponding next flank. The instrument is used as a comparator from which we can calculate the adjacent pitch errors, actual pitch and accumulated pitch errors. Summary, which is the last slide of this chapter. Gears are the main elements in transmission systems. For efficient transfer of speed, uh, power, gear should conform perfectly to the design profile and dimension. During measuring manufacturing, the gears are inspected to ensure high degree of accuracy using difference method. All methods compromising general testing methods and measurement of different elements of gears are discussed in this chapter. So, for better understanding, the PDF of this chapter has been uh, uploaded, link has been uploaded in the comment section. So, you may refer for proper visibility. Thank you.